Hexagons are nature's perfect shape. Bees use them to store honey with the least wax. Graphene, the strongest material we know, is one atom-thick sheet of them. Snowflakes lean on them. They tile a floor with zero waste, no gaps, no overlaps. So obviously, that's what a soccer ball is made of. Except it isn't. It can't be. And the proof is 4 lines long, short enough to fit on a napkin, powerful enough to be inescapable. By the end of this video you'll know why every soccer ball has exactly 12 pentagons, not because a designer liked the look, not because it photographs well, but because math left them no choice. 12. Always 12. Never 11, never 13. Whether the ball is huge or tiny, cheap or professional, the count never budges. Hold on to that number. It's going to be the punchline, and it's going to show up again in places you would never expect. The classic ball, the Telstar, from the 1970 World Cup, has 12 black pentagons and 20 white hexagons. 32 faces in total. It was designed to be visible on black and white television, and it became the template every ball since has borrowed from. And your first reasonable question is, why complicate it? Why bother with 2 different shapes at all? Hexagons already tile a flat surface perfectly, effortlessly, forever. So why doesn't that same trick just work on a ball? Here's where it gets interesting. Picture a honeycomb. At every corner, exactly 3 hexagons meet. Not 2, not 4, 3. Each hexagon's interior angle is 120 degrees. 3 of them together, 120 times 3 equals exactly 360. A full circle, completely flat. There's no wiggle room, no leftover angle, nothing to spare. Every corner is already using up all the angle it possibly can, which means there is nothing left over to bend anything into a curve. But a sphere isn't flat. To curve a flat sheet into a ball, you have to remove some angle at the corners, pucker it, like darts sewn into a tailored shirt to make flat cloth hug a curved body. You need spots where the angles don't add up to 360, where a little slice is missing so the surface can fold up on itself. Mathematicians call that missing slice an angular deficit. And a hexagon, sitting at a perfect flat 360, gives you a deficit of exactly 0. No missing slice, no fold. So a floor of pure hexagons stays a floor, forever. It quite literally refuses to close. But maybe that's just hard to visualize. Maybe the hexagons don't have to be regular. Maybe with enough clever bending, some tiny distortion here and there, it could still close up into a ball. It feels like it should be possible if you're stubborn enough. So let's stop hand-waving and actually prove it can't. Not probably can't. Not seems hard, but genuinely, provably impossible. There's a twist coming that kills the idea permanently, and it comes from an unexpected direction. Enter Leonhard Euler, 1758, with one of the most beautiful formulas in all of mathematics. Take any solid shape without holes, a cube, a pyramid, a soccer ball, a lump of clay, whatever you like. Count 3 things: the vertices, the corners, the edges, the lines between them, and the faces, the flat panels. Then compute vertices minus edges plus faces. And no matter what shape you chose, you always get the same answer. You always get 2. Let's check it ourselves. A cube. 8 corners, 12 edges, 6 faces. 8 minus 12 plus 6 equals 2. A tetrahedron. A triangular pyramid. 4 corners, 6 edges, 4 faces. 4 minus 6 plus 4 equals 2. An octahedron. A dodecahedron. Try them all. They every one land on 2. And it doesn't matter how you deform the thing, squash it, stretch it, dent it like a soda can, as long as there's no hole punched through it, the answer stays stubbornly, boringly, reliably too. Now here's the wild part. Watch what happens when we simply assume a ball made of hexagons only, and let the counting do the talking. Every hexagon has 6 edges, but each edge is shared between 2 neighboring faces, so if you just multiply 6 by the number of faces you've double counted every single edge. So total edges equals 6 times the number of faces, divided by 2, that's E equals 3F. Now the corners. Every hexagon has 6 corners, and each corner is shared by 3 faces meeting there. So vertices equals 6F over 3, V equals 2F. 2 clean little facts, no assumptions beyond all hexagons. Now feed those 2 facts into Euler. V minus E plus F becomes 2F minus 3F plus F. The F's just collapse, that's 0. Clean, exact 0. No matter how many faces you have. And Euler, who is never wrong about this, says it must equal 2. 0 does not equal 2. That's a contradiction. 4 lines of algebra, and every hexagon-only soccer ball in the multiverse just quietly died. It isn't difficult to build. It isn't expensive. It's impossible. The universe filed the paperwork in 1758 and never told the manufacturers. So hexagons alone are out. The pattern needs help. Pentagons are the classic fix, and you can already see them on every real ball. But that raises two sharper questions. Exactly how many pentagons do we need to bend a flat sheet into a closed ball? And, more mysteriously, why is the answer always the same number, no matter the size or style of the ball? Remember that number I told you to hold on to? Here's where it finally earns its keep. There's a companion theorem, older than Euler's, from René Descartes, and it's genuinely gorgeous. Add up all the angular deficit across a closed convex shape, every little pucker, every missing slice at every corner, and it always totals exactly 720 degrees. 2 full turns. Not approximately, not on average, exactly 720, every time. It doesn't matter if it's a sharp-cornered cube, a lumpy boulder, or a smooth ball. The total curvature is fixed, 720. Arithmetic doesn't take bribes. So how much deficit does one pentagon actually buy us? A regular pentagon's interior angle is 108 degrees, a little smaller than the hexagon's 120. Slot a pentagon in among the hexagons, and at each of its 5 corners you get one pentagon and 2 hexagons meeting. 108 plus 120 plus 120 equals 348. That's 12 degrees short of a flat 360. 12 degrees of deficit, 12 degrees of genuine curvature, at each of the pentagon's 5 corners. And 5 corners times 12 degrees each is 60 degrees of curvature contributed by every single pentagon. See where this goes? Descartes told us we need 720 degrees of total deficit to close any convex shape. And each pentagon delivers exactly 60 of those degrees. So the number of pentagons is just 720 divided by 60, which equals 12. Exactly 12 pentagons. Not 11, not 13, not about a dozen. 12, every single time, forced by 2 theorems agreeing with each other. There's your number, and now you can see it was never a design decision at all. And this is why the pattern isn't a choice. Insert one pentagon into a flat hexagonal sheet and it bows upward. It stops being flat the instant you do it. Insert a few more and the surface curves harder, cupping into a bowl. Insert more still and the bowl deepens. And at exactly 12, with 720 degrees of curvature spent, it seals shut into a complete sphere. The pentagons aren't decoration. They aren't a stylistic flourish. They are the load-bearing curvature, the structural elements that make a ball a ball. The specific object you get has a name, and I want you to say it with the reverence it deserves, the Truncated Icosahedron, which is a very fancy way of saying soccer ball. Here's how you build one. Start with an icosahedron, 20 triangular faces, and 12 pointy corners where 5 triangles meet. Now slice off every one of those corners with a clean cut. Each sliced-off corner leaves behind a little pentagon, and each original triangle, with its 3 tips trimmed, becomes a hexagon. 12 corners means exactly 12 pentagons. There's that number again, plus 20 hexagons, 60 vertices, and 90 edges. Let's audit Euler one more time, just to be sure the ball is honest. 60 vertices, minus 90 edges, plus 32 faces, that's 12 pentagons and 20 hexagons added together. 60 minus 90 plus 32. That's 2. The formula holds perfectly. The ball closes, the curvature balances, the counting agrees with itself, and somewhere Leonhard Euler is quietly smiling. Now here's where it gets genuinely strange. This whole story isn't just about sports equipment or stitched leather. The exact same shape, governed by the exact same theorems, shows up across 10 orders of magnitude, from things smaller than you can see to things you could walk inside. Nature keeps rediscovering it independently, because it isn't a fashion. It's a mathematical requirement, and math doesn't care whether you're a molecule or a stadium. In 1985, chemists found a carbon molecule, 60 atoms, arranged in precisely this pattern. 12 pentagons, 20 hexagons, a molecular soccer ball less than a nanometer across. They named it Buckminster-Fullerene, the Buckyball, after the architect Buckminster Fuller. It opened up an entire new branch of chemistry, and it won the 1996 Nobel Prize. The prize, naturally, went to the discoverers. Euler, who quietly dictated the shape 3 centuries earlier, got exactly nothing. It keeps going, and it gets weirder. Many viruses build their protective protein shells as icosahedral capsids, beautiful geometric cages, and how many pentagonal units are needed to close every one of them? 12. Geodesic domes, the ones architects still proudly call innovative, are triangulated spheres that need exactly 12 pentagonal points to curve their triangles into a dome. And try to force flat graphene into a ball, and you literally have to introduce pentagonal rings into the lattice to bend it. Same constraint, every single time. A soccer ball, a virus, and a dome all obey the exact same theorem, whether they know it or not. Which brings us to the part nobody says out loud. FIFA has never once credited Euler. No statue, no plaque, no asterisk on the ball. Marketing departments unveil each new World Cup ball as revolutionary, reimagined, The most advanced ball ever, and every single time, underneath the paint, it's a truncated icosahedron. The man mathematically authored their flagship product 260 years before they started selling it, and he hasn't seen a single cent in royalties. The greatest silent partner in sports history. And here's the loose thread I'll leave you with. That number 2 in Euler's formula isn't random, and it isn't special to spheres just because. It has a name, the Euler Characteristic, and it secretly describes the shape of a surface itself. A sphere's characteristic is 2. But a donut? A donut is 0. And that single difference between 2 and 0 turns out to change absolutely everything about what you can tile the surface with. Because a donut needs 0 total curvature to close, unlike a sphere, you actually can tile a donut with hexagons alone, no pentagons required at all. The number is really counting holes. That is the doorway into topology, and into the question we asked in our video on the shape of the universe: if a sphere is 2, what on earth is the characteristic of everything? We'll come back to that donut another day. For now, 12 pentagons, mathematically inevitable, hiding in plain sight at every World Cup, in every virus, in every Buckyball. If you enjoyed this, subscribe to Improper Integral for more visual math and science. We did the game theory hiding inside penalty shootouts last time, and the ball itself turned out to be just as deep. And next time you see that ball, remember, nobody designed the pattern. Euler did, and he wasn't even trying.